In the constellation Leo 124, light-years away, a significant discovery has been made concerning a world that orbits a red dwarf star and is dissimilar to any in our solar system. This finding pertains to the long-standing question of whether humanity is alone in the universe. The atmosphere of a planet named K2-18b may hold the answer, and discoveries made by the James Webb Space Telescope are considered revolutionary. This is more than a typical exoplanet discovery, as it challenges previous assumptions about where life can exist. The planet belongs to a category so new that new terminology was created to describe it. Molecules detected in its atmosphere have caused scientists to either celebrate the finding or re-examine their data. The James Webb Space Telescope detected water vapor methane and carbon dioxide. However, the most significant detection is of a molecule that, based on our understanding of Earth, is produced exclusively by living organisms. This chemical signature could be the first real indication of life beyond our solar system. The Kepler Space Telescope first detected K2-18b in 2015. What was initially a routine detection later proved to be a more profound discovery. Classified as a sub-Neptune, K2-18b is a type of planet intermediate between rocky planets like Earth and gas giants like Neptune. Its radius is approximately 2.5 times that of Earth, and its mass is nearly 9 times greater. The planet is located in its star's habitable zone, where conditions may be suitable for liquid water. K2-18b orbits its red dwarf star every 33 days, and due to the star's cool temperature, the planet receives a similar amount of energy as Earth does from the Sun. K2-18b is not a rocky planet. It belongs to a new class of potentially habitable planets called Haitian worlds, a term derived from hydrogen and ocean. These worlds are characterized by extensive liquid water oceans beneath thick hydrogen atmospheres. Previously, planets with hydrogen-rich atmospheres were considered too hot for life due to a strong greenhouse effect. However, recent models suggest that under specific conditions, these atmospheres could regulate temperatures, permitting the existence of liquid oceans. This world could have an ocean larger than all of Earth's combined, under a thick hydrogen atmosphere with pressures many times greater than on our planet. The James Webb Space Telescope has studied this planet with high precision, and its findings are causing astronomers to reconsider the known requirements for life. To study K2-18b, the telescope used transmission spectroscopy using the planet's star as a backlight. As the planet transited, its starlight filtered through its atmosphere. Molecules within the atmosphere absorbed specific wavelengths, creating a chemical fingerprint that indicates its composition. Scientists analyzed the infrared spectrum for molecular signatures that could suggest the presence of life. The analysis revealed that the atmosphere is primarily hydrogen, which is consistent with its classification. It also contains water vapor, carbon dioxide, and methane. The absence of ammonia supports the hypothesis of a liquid water ocean. This combination of chemicals aligns with theoretical models for a Haitian world. The presence of methane and carbon dioxide, alongside the lack of ammonia, indicates possible chemical interactions between the atmosphere and an ocean. Furthermore, the spectroscopic data contains a faint signal at the limit of detection. If confirmed, this molecular signature would be the most compelling evidence for extraterrestrial life found to date. The detected molecule is dimethyl sulfide, DMS. On Earth, DMS is produced almost exclusively by biological processes, primarily by marine phytoplankton. It is considered a biosignature because, unlike substances such as oxygen or methane that can have non-biological origins, DMS is known on Earth to be produced only by life. The DMS detection on K2-18b is considered preliminary, with a 3 sigma level of statistical significance, which corresponds to a 0.3% probability that the signal is a false positive. For a discovery to meet the scientific gold standard, it must reach 5 sigma significance. Despite being preliminary, this detection is an unprecedented event in the search for extraterrestrial life, as it is the first time such a strong biosignature candidate has been found in an exoplanet's atmosphere. Dr. Niku Madhusudan of Cambridge University, who led the research, clarified that his team is not claiming to have found life, but rather the potential for life. This cautious statement reflects the scientific standard that extraordinary claims must be supported by extraordinary evidence. While the detection of DMS on K2-18b is a significant finding, it is not yet considered definitive. A complication arises because dimethyl sulfide, DMS, while primarily produced by life on Earth, may not have the same origin elsewhere in the universe. Recent studies indicate that DMS can be created through non-biological processes. It has been found in comets, which are ancient frozen remnants from the early solar system, where life as we know it is impossible. Furthermore, laboratory experiments show that DMS can be formed under prebiotic conditions through chemical reactions that do not involve living organisms. This presents a significant challenge for scientists interpreting the data from K2-18b. The atmospheric DMS concentrations detected on the planet are thousands of times higher than those on Earth. If life on K2-18b is the source, it is operating at a scale and concentration far beyond our terrestrial experience. Alternatively, unknown chemical processes in the unique environment of a Hycean world involving a hydrogen-rich atmosphere and potential oceans could generate DMS through geological or atmospheric means. This uncertainty has divided the astronomical community. Some researchers are cautiously optimistic, considering this the most promising biosignature detections so far, and advocating for more observations to validate the finding. Others remain skeptical, citing the marginal statistical significance and the potential for non-biological sources. This debate highlights a fundamental tension in astrobiology between the ambition to find life and the necessity of scientific rigor, because the discovery of life beyond Earth would be a historically significant event that would alter our understanding of our place in the cosmos. Absolute certainty is required before any such claim can be made. The James Webb Space Telescope, JWST, is the most powerful instrument available for investigating such questions. With its 6th 5-meter mirror, it gathers infrared light with exceptional sensitivity, enabling astronomers to identify molecular signatures in exoplanet atmospheres that were previously undetectable. Unlike the Hubble Space Telescope, which observes mainly invisible light, the JWST was specifically built to search for biosignatures in the infrared spectrum. This is critical because many molecules associated with life, such as water vapor, carbon dioxide, methane, and potentially DMS, exhibit their strongest absorption features at these wavelengths. The telescope's ability to achieve precision, better than 1 part in 10,000 during transit observations, has revolutionized exoplanet science. As K2-18b transits its host star, a small amount of starlight passes through its atmosphere, carrying information about its chemical makeup. The JWST can detect variations in this light that are smaller than the fluctuations of a stable LED bulb. This remarkable precision made the potential DMS detection possible, as the signal is extremely faint and at the very edge of the instrument's capabilities. This achievement reflects both the power of the JWST and the dedication of the research teams who meticulously analyze the data. However, precision alone cannot confirm life on K2-18b. The detection must be repeatable, statistically significant, and supported by a theoretical model explaining how such high DMS concentrations could be produced and sustained. Consequently, future observations are essential. The research team has proposed specific instruments and observation methods to increase the detection's confidence, from its current 3 sigma level to the 5 sigma threshold required for a scientific discovery. More observation time with the JWST's most sensitive spectrographs could provide a definitive answer regarding the presence of dimethyl sulfide in K2-18b's atmosphere. The implications of confirming DMS on K2-18b would be significant, extending beyond this single planet. Sub-Neptunes like K2-18b are among the most common planets in our galaxy. If these Hycean worlds can support life-habitable planets may be much more abundant than previously thought. Traditional searches for habitable exoplanets have concentrated on Earth-like rocky worlds within the zone where liquid water can exist. Hycean planets, however, broaden the definition of habitability to a previously overlooked class of worlds. These ocean worlds, enveloped in hydrogen, could remain habitable at distances where rocky planets would freeze, as the greenhouse effect of their thick atmospheres could maintain liquid oceans. This suggests the habitable zone around stars could be considerably larger, potentially doubling or tripling the number of worlds where life might arise. The study of K2-18b also highlights the immense diversity of planetary atmospheres, revealing new possibilities for atmospheric chemistry and expanding our understanding of life-supporting environments. As we explore the cosmos with more advanced instruments, we are learning that the universe is more varied than our Earth-based perspective suggested. K2-18b is just at the forefront of this discovery process, challenging our assumptions about habitability and potentially answering one of humanity's most fundamental questions. The difficulties in studying K2-18b are not limited to the technical challenges of detecting molecules over vast distances. Researchers are attempting to understand an alien world using instruments and models based on Earth's atmosphere and chemistry. This endeavor involves analyzing light that has traveled for 124 years to determine if microscopic organisms exist in an alien ocean under a hydrogen sky, an effort that pushes technology to its limits. The atmospheric models used to interpret K2-18b's spectroscopic data are heavily based on our understanding of physics and chemistry under terrestrial conditions. However, the exotic environments of Hycean worlds might render this experience inadequate. The pressures, temperatures, and chemical interactions in K2-18b's atmosphere could lead to novel pathways for molecular formation. This uncertainty is particularly relevant given the potentially high concentrations of dimethyl sulfide, which are thousands of times greater than those on Earth. If life is responsible, it would have to be producing these molecules on a scale that surpasses the entire biomass of Earth's oceans. Dr. Eddie Schweitman of UC Riverside, an expert in biosignatures and atmospheric chemistry, has noted that such extreme concentrations raise significant questions about the plausibility of the life hypothesis. On Earth, phytoplankton produce dimethyl sulfide, DMS, in small amounts, which is then quickly degraded by atmospheric chemistry. For K2-18b to have such high concentrations, its production must be highly efficient, or its breakdown processes must be very limited. The chemistry of a hydrogen-dominant atmosphere might make DMS more stable than it is in Earth's oxygen-rich environment. Hydrogen atmospheres lack the reactive hydroxyl radicals that break down many organic molecules, which could allow biosignature gases to accumulate in higher concentrations than on our planet. Alternatively, A hydrogen-rich environment might support different biochemical pathways that produce DMS through processes not seen on Earth. Life can adapt to extreme conditions, and any organisms in K2-18b's oceans might have evolved metabolisms entirely different from those on Earth. The chance of a false positive is a major consideration in discussions about K2-18b's potential biosignature. The history of astrobiology contains many promising findings that were later explained by non-biological phenomena. In 1976, the Viking missions to Mars detected what seemed to be biological activity in soil, but this was later attributed to unexpected soil chemistry. More recently, the detection of phosphine in Venus's atmosphere led to speculation about microbes until alternative production methods were suggested. These experiences have led the astronomical community to be skeptical of biosignature detections, requiring multiple lines of evidence before making significant claims. The DMS detection on K2-18b, though interesting, is just one part of the larger body of evidence needed to confirm the existence of life. A significant challenge comes from the limitations of remote sensing. K2-18b can only be studied during the brief periods it passes in front of its star, and even then, the analysis relies on subtle changes in the star's light. These observations give a snapshot of the planet's atmospheric chemistry, but do not provide information on variations over time, spatial distribution, or the processes behind chemical production. On Earth, biosignatures, like DMS, vary with seasons, locations, and ecological conditions. For instance, phytoplankton blooms can temporarily increase DMS production, while ocean temperature and chemistry affect its atmospheric lifespan. It is not known if similar variations occur on K2-18b or how they might influence the interpretation of spectroscopic data. The research team, led by Dr. Madhusudan, acknowledges these uncertainties while remaining cautiously optimistic. They have planned follow-up observations to either confirm or refute the DMS detection, including longer observations with the James Webb Space Telescope's most sensitive instruments and observations at different wavelengths for independent confirmation. These future observations are a critical test of the biosignature hypothesis. If DMS is present at the levels suggested, more detailed observations should detect it with higher statistical significance. If the initial detection was a false positive, further observations will not confirm its presence. The timing of these observations depends on the competitive scheduling for the James Webb Space Telescope. While K2-18b is one of many high-priority targets, the importance of confirming or refuting a biosignature makes it likely that more observation time will be allocated to this system. While awaiting these observations, theoretical work is being done to understand how life might exist in Haitian environments. The conditions on K2-18b would be very different from those on Earth, requiring life to adapt to high atmospheric pressures, hydrogen-rich chemistry, and possibly different ocean compositions. Some researchers are studying Earth's extremophiles, organisms that thrive in harsh conditions, for clues about life on Haitian worlds. Examples include deep-sea bacteria near hydrothermal vents and microorganisms in highly acidic or high-pressure environments, which show life's adaptability. Laboratory experiments are being set up to test if terrestrial microorganisms can survive and reproduce under conditions like those on K2-18b. These experiments involve exposing bacteria and archaea to hydrogen-rich atmospheres, high pressures, and altered ocean chemistry to see if they could serve as models for Haitian life. The results could help interpret the K2-18b data by suggesting possible metabolisms and biochemical pathways. If Earth organisms can adapt to and produce molecules like DMS in such environments, it would support a biological explanation for the spectroscopic data. The implications of discovering life on K2-18b extend beyond astrobiology to fundamental questions about the nature of life in the universe. For many years, the search for extraterrestrial life has been guided by looking for liquid water on planetary surfaces. The discovery of habitable Hycean worlds would change this approach. If life can exist in the oceans of sub-Neptune planets, the number of potentially habitable worlds in our galaxy could increase significantly. Sub-Neptunes are one of the most common types of exoplanets, and their host red dwarf stars are the most numerous in the Milky Way. This could mean that Hycean worlds are the most common type of habitable environment. This has significant implications for the Drake equation, which estimates the number of communicating civilizations. If Hycean worlds can support life that evolves to be intelligent, the universe might be much more populated than previously thought. The detection of life on K2-18b would also lead to questions about finding similar biosignatures on other sub-Neptune exoplanets. Astronomers have already found many other sub-Neptunes in their star's habitable zones that could be targets for biosignature searches with current and future telescopes. Finding life signatures on multiple worlds would shift astrobiology from just detecting life to understanding its diversity and distribution. Each world would likely have unique ecosystems adapted to its specific conditions, creating a wide variety of life. Despite these possibilities, the scientific community remains committed to rigorous analysis. The potential DMS detection on K2-18b is a promising lead, but requires careful investigation. The next few years will be crucial in determining if K2-18b has biosignatures indicating life, or if the signals are from unknown chemical processes in an exotic atmosphere. Either result will further our knowledge of planetary atmospheres and the possibility of life in the universe, though only one would resolve the long-standing question of whether humanity is alone. With ongoing observations from the James Webb Telescope and increasingly sophisticated theoretical models, we are approaching answers that could reshape our perception of our position in the cosmos. K2-18b has demonstrated that the universe is more unusual and varied than previously thought, and it may also disclose whether this includes the chemistry of life. The narrative behind this significant discovery is as compelling as the finding itself. When the James Webb Space Telescope initially targeted K2-18b, astronomers did not anticipate making a potentially historic discovery. Their work was part of a routine atmospheric study of a sub-Neptune, contributing to a larger survey aimed at understanding the differences between these common enigmatic planets and those in our solar system. These observations demanded considerable patience and precision. Analyzing an exoplanet's atmosphere, unlike imaging a galaxy, requires exact timing. Researchers needed to wait for K2-18b to transit or pass directly between its star and Earth, an event that takes place every 33 days. This observation window lasts for only a few hours. In that short time, the James Webb Telescope gathered light that had journeyed 124 light-years and been filtered through K2-18b's atmosphere, thereby carrying its chemical signatures. The collected data consisted of numerical streams of wavelengths and intensities, which held chemical information that required months of analysis by atmospheric chemists. Dr. Madhusudan's team dedicated extensive time to examining this data for absorption lines, which indicate the presence of specific molecules in K2-18b's atmosphere. Every molecule possesses a distinct signature in the infrared spectrum, serving as a unique identifier. For instance, water vapor, carbon dioxide, and methane. Each produce their own specific patterns of absorption lines at different wavelengths. Initially, the findings were promising, but not groundbreaking. The presence of water vapor was expected based on models of Hycean worlds. The detection of carbon dioxide and methane also aligned with predictions for this kind of Planet A. Low level of ammonia supported the theory of liquid oceans under the hydrogen atmosphere. However, an unanticipated signal was found within the data corresponding to none of the expected molecules. Researchers first suspected the signal could be an error from the instrument or contamination from Earth's atmosphere, as space telescopes can detect terrestrial gases on the spacecraft. However, after further analysis, which involved comparing multiple observations and ruling out errors, the signal remained. The wavelengths were consistent with those of dimethyl sulfide. The significance of this potential finding was so great that the team invested months in repeated verification before considering publication. Peer review provided additional scrutiny with independent scientists evaluating the data analysis, questioning the statistical methods, and suggesting other explanations for the signals. This thorough review process is a fundamental strength of science. Some reviewers proposed that the dimethyl sulfide signal could be from other molecules with similar spectroscopic properties, while others doubted its statistical significance. The research team systematically addressed every point, refining their analysis and acknowledging remaining uncertainties. The publication of their findings initiated a broader scientific discussion. Other research groups quickly began independent analyses of the public data, with some corroborating the findings and others remaining skeptical about the interpretation. This scientific debate highlights the importance of the claim, as a confirmed biosignature would be one of the most significant discoveries in scientific history, changing our view of life in the universe. Such a claim requires exceptional scrutiny, and the scientific community has responded with appropriate rigor. Theoretical research is now exploring potential life forms on K2-18b. The environmental conditions, such as atmospheric pressure, potentially dozens of times higher than Earth's sea level, would resemble our deep ocean trenches. A hydrogen-rich atmosphere would necessitate different biochemical reactions, requiring life to use alternative methods for energy and molecular synthesis. Some scientists suggest that such an environment could offer benefits. For example, the lack of reactive oxygen might lead to less cellular damage and longer lifespans. The high pressure could facilitate more effective gas exchange, and the large oceans could offer a vast habitat, possibly supporting extensive and diverse ecosystems. The possible detection of dimethyl sulfide on K2-18b has also led to new research into the molecule's behavior in unusual environments. Laboratory experiments are being set up to determine if non-biological processes could produce dimethyl sulfide under the high-pressure, hydrogen-rich conditions of Hycean worlds. This involves simulating K2-18b's atmosphere in special chambers to observe chemical reactions. In parallel, computational models are being created to simulate the intricate chemistry of K2-18b's atmosphere and oceans, studying how molecules might interact in an environment unlike any in our solar system. These theoretical tasks are challenging due to the extreme and unfamiliar conditions. Nevertheless, this work is vital for interpreting the observational data, as the combination of theory and observation will be necessary to distinguish between evidence of life and the effects of unusual atmospheric chemistry. Studying planets like K2-18b has driven the development of advanced instrumentation. The level of precision required to identify potential biosignatures over interstellar distances necessitates spectrographs capable of measuring wavelengths with an accuracy of parts per billion. To track subtle changes over multiple observations, thermal control systems must maintain temperatures with millikelvin stability. The James Webb Space Telescope represents the current peak of this technology, yet it operates at the limits of what is required for definitive biosignature detection. Future space telescopes are therefore being designed with greater sensitivity and precision, which could allow them to detect biosignatures with the statistical confidence needed for scientific certainty. Complementing these space-based observations, the extremely large telescopes currently being built on Earth will feature enormous mirrors to collect vast quantities of light. This capability will enable detailed spectroscopic studies of exoplanet atmospheres at unprecedented resolutions. The combination of observations from both space and the ground could provide the multiple lines of evidence required to confirm or refute potential biosignature discoveries. The implications of such a discovery extend far beyond astronomy and astrobiology. Finding life beyond Earth would fundamentally change philosophy, religion, and our understanding of our place in the universe. It would immediately raise questions about the nature and origins of that life and its relation to terrestrial biology. It would need to be determined if life on K2-18b shares a common ancestry with organisms on Earth, which would suggest a cosmic seeding process, or if it represents an independent genesis, proving that life is a natural outcome of chemistry under suitable conditions. These questions would drive scientific inquiry for generations. The detection of life on K2-18b would also significantly affect the search for intelligent life. If simple organisms can exist in the environments of Haitian worlds, it raises possibilities for what could occur over millions or billions of years of evolution. Intelligence could potentially emerge from such alien biospheres, leading to technological civilizations different from what we can imagine. These ideas have led some researchers to suggest listening for signals from Haitian worlds in addition to Earth-like planets. Organizations like the SETI Institute, which are dedicated to searching for extraterrestrial intelligence, are starting to re-evaluate their search strategies in light of the possibility that life may be common on sub-Neptune exoplanets. However, the possibility of communicating with life on K2-18b presents immense practical difficulties. The distance of 124 light-years means a round-trip signal would take nearly 2.5 centuries. A conversation, even if intelligent life existed and was attempting to communicate, would occur on timescales far exceeding those of human civilization. Despite this, the mere knowledge that life exists elsewhere would transform humanity's perspective. We would no longer be alone in the universe or unique in our capacity to contemplate the cosmos. The consequences would affect all aspects of human culture, and understanding religious traditions would need to adapt their cosmologies to include extraterrestrial life. Philosophers would debate the discovery's meaning for concepts of purpose in the universe. Artists and writers would find new inspiration in the possibilities of alien life. Educational systems would have to integrate astrobiology into their curricula to prepare future generations for a universe known to contain life beyond Earth. The discovery would also likely stimulate major investment in space science and exploration, leading to significant economic effects as humanity seeks to learn more about cosmic neighbors and potentially develop interstellar travel technologies. The space industry would expand rapidly as governments and private entities invest in the telescopes, spacecraft, and technologies required to study distant worlds. This would lead to the emergence of new research fields and create career opportunities for scientists, engineers, and technicians in astrobiology and exoplanet science. Most profoundly, finding life on K2-18b would highlight how much remains unknown about the universe. Each discovery seems to generate more questions, expanding the scope of cosmic mystery. As we await future observations to confirm or deny the potential biosignature on K2-18b, we are on the verge of what could be the greatest discovery in history. The coming years may confirm that we share the universe with other life forms, which would fundamentally alter our understanding of being alive. Light from K2-18's host star continues to travel to Earth, carrying information about a world that may harbor life. Every photon that our telescopes collect brings us closer to answering the long-standing question of whether we are alone. The effort to understand K2-18b's potential for life has shown the limits of current scientific technology. When astronomers began analyzing the spectroscopic data from this world, they were entering new territory. The molecules being sought were in such low concentrations that detecting them was exceptionally difficult. The precision required for these measurements is extraordinary. Variations in starlight that reveal the planet's atmospheric composition are equivalent to changes of only a few parts per million in the star's total brightness. This level of precision is achievable only through significant advancements in infrared detector technology and data processing algorithms. The sensors on the James Webb Space Telescope are cooled to just a few degrees above absolute zero to minimize thermal noise to levels unattainable by previous space telescopes. The data processing systems can then identify and correct for minor systematic errors that would otherwise obscure the faint signals from an exoplanet's atmosphere. Even with this advanced technology, detecting potential biosignatures on K2-18b took months of detailed analysis. Research teams had to account for numerous sources of error, from cosmic ray impacts on the detector to small variations in the telescope's pointing stability. Each potential error source needed to be identified, modeled, and subtracted from the data to reveal the true atmospheric signals. This process is further complicated because the atmosphere being studied is unlike any in our solar system. The chemical interactions in K2-18b's hydrogen-rich environment may follow pathways not observed in terrestrial laboratories. Its pressure and temperature conditions might allow for molecular formations that are not possible on Earth. Dr. Sarah Seeger of MIT, a pioneer in exoplanet atmospheric characterization, has likened the challenge to decoding a message in a language that is still being learned. Each spectroscopic line is a word, but the chemical rules on Hycean worlds might differ fundamentally from those on Earth. This language metaphor is especially relevant when considering potential false positives for the DMS detection. Just as words in different languages can sound alike but have different meanings, the absorption lines of different molecules can overlap and create misleading signals. Research teams had to systematically rule out many alternative explanations for the observed spectroscopic features. One of the greatest challenges in interpreting K2-18b's atmospheric data is the large number of variables involved. The planet's atmosphere is a complex and dynamic system in which temperature, pressure, and chemical composition change with altitude, latitude, and time. Spectroscopic observations provide a limited view of the K2-18b system, representing an average of the planet's visible surface over the few hours of transit. On Earth, atmospheric scientists utilize a network of weather station satellites and aircraft to create three-dimensional maps of our atmosphere's structure and composition, enabling them to monitor how gas concentrations fluctuate with seasons, weather, and human activity. For K2-18b, all this detailed information is condensed into a single spectrum that must be used to understand the atmospheric chemistry of an entire world. The statistical methods for extracting information from such limited data have become more advanced. Machine learning algorithms trained on large databases of laboratory spectra can identify subtle patterns that human analysts might overlook. Bayesian statistical techniques allow researchers to measure the uncertainty in their measurements and compare the likelihood of different explanations for the observed signals. These advanced analytical methods have revealed a surprisingly complex atmospheric composition on K2-18b. In addition to the widely reported potential detection of DMS, the planet's spectrum indicates the presence of other molecules that could offer more clues about the conditions on this distant world. The presence of trace amounts of sulfur-bearing compounds, organic molecules, and other unusual chemical species suggests an atmospheric chemistry that is both unfamiliar and intriguing. The sulfur chemistry in K2-18b's atmosphere is a specific area of research interest. On-Earth sulfur is essential for both biological and geological processes, moving through the atmosphere, oceans, and crust in complex cycles that have developed over billions of years. The detection of several sulfur-bearing molecules on K2-18b suggests that similar cycles may be occurring there. Although the specific processes could be very different, some researchers suggest that the sulfur compounds on K2-18b might be produced by hydrothermal activity on the ocean floor, similar to the deep-sea vents that support unique ecosystems in Earth's oceans. These underwater volcanic systems could supply the chemical energy required for biological processes, creating pockets of life in the dark depths under K2-18b's hydrogen atmosphere. The idea of hydrothermal activity on K2-18b leads to interesting questions about the planet's internal structure and geological past. Unlike rocky planets such as Earth, where plate tectonics and volcanic activity are powered by radioactive decay in the core, the internal processes of sub-Neptune planets are not well understood. The immense pressure from K2-18b's large atmosphere might compress the ocean below to such a degree that new states of matter could form at the boundary between liquid and solid. Recent theoretical studies have proposed that the cores of sub-Neptune planets could be made of unusual forms of ice that only exist under extreme pressure. These superionic ices could conduct electricity like a metal while retaining the molecular structure of crystalline water. The interaction between these unique core materials and the ocean above could lead to chemical processes not seen on Earth. The potential for a magnetic field resulting from these unique internal structures is also of great interest. If K2-18b's core has electrically conductive materials, the planet might create a magnetic field that could shield its atmosphere from being stripped away by stellar radiation. Red dwarf stars, like the one K2-18b orbits, are known for producing strong flares that can erode planetary atmospheres over long periods. A protective magnetic field would be vital for maintaining a stable atmospheric chemistry that could support life. Without this protection, any potential biosignature molecules from hypothetical organisms would be quickly broken down by high-energy particles from the host star. Therefore, the persistence of complex molecules in K2-18b's atmosphere could be indirect evidence of a magnetic field and consequently internal geological activity. These points demonstrate how the search for life on K2-18b has grown into a broad study involving multiple scientific fields. Determining if this world could support life requires knowledge from atmospheric chemistry, geology, magnetospheric physics, and astrobiology. Each element of this puzzle must align for the hypothesis of life to be considered plausible. The interdisciplinary nature of this research has led to new collaborations among scientists who typically work separately. Atmospheric chemists are now working with geologists to understand how interactions between the surface and ocean might impact gas levels. Magnetospheric physicists are partnering with astrobiologists to model how stellar radiation could affect the survival of potential life forms. Computer scientists are creating new algorithms to get the most information from limited observational data. This collaborative effort has already produced findings that apply beyond K22 or 18b. The methods developed to analyze this planet's atmosphere are now being used for other exoplanet systems, building a larger database of atmospheric compositions and highlighting the vast diversity of worlds outside our solar system. Each new observation contributes to our understanding of how planetary atmospheres form and what conditions might be required for life to begin and survive. The comparative study of planets has shown that while K2-18b is unique in several ways, it also has similarities with other sub-Neptune exoplanets in the habitable zones of their stars. This increasing number of potentially habitable worlds is revealing patterns that could help identify the most important factors for creating life-sustaining conditions. Some sub-Neptunes have clear signs of water vapor, while others seem to have atmospheres dominated by heavier gases like carbon dioxide or methane. These variations may be due to factors such as how the planets formed, their distance from their host stars, or the composition of the disks from which they originated. Understanding these connections could help predict which newly found exoplanets are most likely to show signs of life. The technological advancements from studying K2-18b are also guiding the development of new space telescopes that will detect biosignatures with even greater accuracy. The upcoming Nancy Grace Roman Space Telescope will provide unique capabilities for exoplanet analysis that will complement the James Webb Space Telescope. Ground-based observatories, like the extremely large telescope, will offer exceptional light-collecting ability for in-depth spectroscopic studies. These future instruments are being designed specifically to achieve the statistical certainty needed to confirm the detection of biosignatures. While current observations may provide a certain level of confidence, future telescopes could offer the high degree of certainty required to announce the discovery of life beyond Earth. The creation of these advanced instruments is a significant investment by the global scientific community to address one of humanity's most fundamental questions. Government space agencies, private foundations, and international partnerships are allocating billions of dollars to develop the necessary tools to find life on other worlds. This investment shows not only scientific curiosity, but also the understanding that such a discovery could fundamentally change our view of our place in the universe. The potential discovery of life on K2-18b has implications that scientists are just beginning to consider. If life can exist and thrive in the unique conditions of Haitian worlds, billions of years of evolution on such planets could lead to unknown outcomes. It raises speculative questions about whether intelligence could develop in oceans covered by hydrogen, or if technological civilizations could emerge in environments so different from Earth that their technologies would be unrecognizable. These ideas are starting to shape how researchers look for technosignatures which are observable signs of alien technology. While traditional SETI programs have concentrated on radio signals from civilizations like our own, the discovery of potentially habitable Haitian worlds indicates that search methods may need to be broadened to include technologies suited for very different environments. The potential for life on K2-18b has stimulated new interest in theoretical biology and the core necessities for living systems. Researchers are investigating if fundamental evolutionary principles, such as natural selection, would function differently in the extreme environments of Hycean worlds. The combination of high atmospheric pressure, unusual chemistry, and large oceans could result in evolutionary forces distinct from those on Earth. Some theories suggest that life in these environments could evolve toward gigantism, achieving sizes unattainable on Earth, due to support from the high atmospheric pressure. Other theories propose that the stable, energy-rich conditions of oceans enveloped in hydrogen could promote the evolution of exceptionally long-lived organisms, potentially creating ecosystems that endure for geological time. Another area of speculation involves the energy sources that hypothetical life on K2-18b could use. While Earth's biosphere is primarily sustained by solar energy through photosynthesis, the dense hydrogen atmosphere of a Hycean planet could significantly block starlight from reaching the ocean's surface. Consequently, life there might need to depend on chemical energy sources. The chemistry of a hydrogen-rich ocean could offer many opportunities for chemosynthetic metabolism, much like the organisms that thrive near Earth's deep-sea hydrothermal vents. Chemical reactions driven by the interaction between hydrogen gas and dissolved sulfur compounds could release energy for biological functions. Furthermore, the high pressures could facilitate chemical pathways that are not energetically favorable under Earth-like conditions, possibly supporting metabolisms that could not exist in our biosphere. Such theoretical investigations assist scientists in determining the types of biosignatures that life adapted to Hycean environments might create. If organisms on K2-18b rely mainly on a sulfur-based metabolism, they could produce different gas combinations compared to Earth's biosphere, which is predominantly based on carbon and oxygen. A thorough understanding of these alternative biochemistries is essential for interpreting atmospheric observations and confirming if detected molecules are genuine indicators of biological activity. The search for life on K2-18b has also emphasized the need to understand false positive scenarios where natural geological or atmospheric events could imitate biological signatures. The solar system provides multiple instances of non-biological processes, producing molecules that could otherwise be mistaken for biosignatures. For example, on Jupiter's moon, Europa, high-energy particles from Jupiter's magnetosphere interact with the moon's ice surface to create hydrogen peroxide through radiolysis. Similar processes involving stellar radiation and cosmic rays might occur on K2-18b, driving chemical reactions that form complex organic molecules without any biological involvement. The volcanic activity on Io, another of Jupiter's moons, shows how geological processes can generate sulfur compounds in concentrations far greater than what biology typically produces. If K2-18b is geologically active, similar volcanic events could explain the sulfur chemistry seen in its atmosphere without needing a biological explanation. These considerations highlight the difficulty of definitively confirming biosignatures in exoplanet atmospheres. Each potential detection must be assessed not only for its statistical significance, but also for its biological plausibility and the existence of alternative explanations. The scientific method requires researchers to eliminate all possible non-biological causes before concluding that life is the most probable reason for observed phenomena. The continuous analysis of K2-18b's atmospheric data is refining our comprehension of these observations. Each new publication on this system adds nuance to the interpretation, sometimes strengthening the case for biology, and at other times suggesting different explanations. This iterative process of hypothesis testing and refinement is how science should operate when addressing questions of such profound importance. The international scope of this research has been remarkable. Teams from many countries have contributed observations, analytical techniques, and theoretical insights to the understanding of K2-18b. The data from the James Webb Space Telescope is publicly available, allowing researchers globally to perform independent analyses and add to the growing knowledge of this world. This open science approach has accelerated progress and ensures that multiple perspectives are applied to interpreting the data. When different research groups, using various analytical methods, reach similar conclusions, it builds confidence in the results. When they disagree, it points to areas where more work is necessary to resolve uncertainties. The collaborative spirit in K2-18b research reflects an acknowledgement that discovering life beyond Earth would be an achievement for all of humanity, not just for the scientists involved. The implications would be so significant that they would affect every person, regardless of nationality, profession, or personal beliefs. At this pivotal moment in the search for extraterrestrial life, the observations of K2-18b represent our best current opportunity to answer the age-old question of whether we are alone in the universe. The potential detection of dimethyl sulfide in this world's atmosphere brings us very close to what could be the most significant discovery in human history. The upcoming months and years will be crucial in determining whether this potential biosignature is authentic evidence of life or simply a reflection of our incomplete understanding of atmospheric chemistry in exotic conditions. Either result will advance our knowledge and prepare us for future discoveries as our observational capabilities improve. In the moments between observations, as the James Webb Telescope continues its patient watch, we are balanced between profound uncertainty and extraordinary possibility. The universe has surprised us before with its complexity and diversity, and K2-18b might hold the greatest surprise of all: the confirmation that life has flourished in the hydrogen-wrapped oceans of a world unlike any in our solar system. The light from this distant world continues its ancient journey to Earth, carrying in its spectral lines secrets that could transform our understanding of life's place in the cosmos. Every photon that reaches our detectors brings us closer to an answer that has eluded humanity throughout our existence. Whether we truly share this vast universe with other forms of life, the debate surrounding K2-18b's potential biosignature reveals something about the nature of scientific discovery itself. We are witnessing science in action as researchers worldwide analyze data that could represent either mundane atmospheric chemistry or the most extraordinary discovery in human history. The process is complex, contentious, and compelling. Dr. Madsudan's team has faced criticism from colleagues who argue that the statistical significance of their DMS detection does not meet the rigorous standards required for such an extraordinary claim. The 3 sigma confidence level, while impressive for most astronomical observations, seems inadequate when weighed against the profound implications of discovering life beyond Earth. This is akin to betting the future of human understanding on a coin toss that lands heads 997 times out of 1,000. Yet this is precisely how science advances at the frontiers of knowledge. Groundbreaking discoveries originate from observations that challenge the limits of our instruments and theoretical frameworks. For instance, the first detection of gravitational waves was met with skepticism until further observations validated Einstein's predictions. Similarly, the discovery of dark energy resulted from observations that appeared to conflict with our knowledge of cosmic expansion, but were later accepted as proof of a new force. Researchers investigating K2-18b are in a comparable situation, feeling both optimistic and cautious about their results. After spending years honing their ability to isolate significant signals from interstellar noise, they're also the first to admit the constraints and uncertainties within their data. This commitment to transparency exemplifies a core principle of scientific research, which requires balancing the excitement of discovery with stringent self-assessment. The scrutiny of the K2-18b research surpasses typical academic review. The possibility of finding extraterrestrial life has captivated the public's interest more than conventional astronomical findings. Consequently, global media coverage has often blurred the line between responsible journalism and sensationalism. This requires the researchers to manage not only scientific obstacles, but also the complexities of public communication and expectations. Although this level of public attention can be unfamiliar for scientists used to relative anonymity, it plays a crucial role in advancing cosmological knowledge. The enthusiasm surrounding potential biosignature detections helps validate the significant public funding allocated to space telescopes and astronomical studies. It serves as a reminder of the motivation for constructing large-scale instruments to explore distant worlds and seek answers to fundamental questions about our cosmic existence. Observations of K2-18b also highlight the sophisticated nature of contemporary astronomical research. The data analysis systems for James Webb observations employ some of the most advanced signal processing methods available, which must correct for factors ranging from minor thermal shifts in the telescope to the slight impact of cosmic radiation on its detectors. An observation of K2-18b produces terabytes of data, requiring meticulous calibration, processing, and analysis to derive scientific insights. This raw data, composed of millions of separate measurements containing small fragments of atmospheric information, looks very different from the refined spectroscopic charts in publications. Converting this data into scientific knowledge is an interdisciplinary process. Instrument experts understand how telescope parts influence the incoming light. Atmospheric physicists create models of molecular infrared absorption. Statisticians design techniques to pull clear signals from noisy data, and computer scientists build efficient algorithms for large data sets. This teamwork is characteristic of the growing complexity in modern astronomy, which necessitates teams of specialists to answer questions that were unapproachable in past decades. Detecting possible biosignatures on remote exoplanets is a prime example of this collaborative method, demanding our most sophisticated technologies and a profound grasp of physics, chemistry, and biology. The K2-18b research has consequences beyond the question of life on that planet alone. The analytical techniques created for its atmosphere are now used on many other potentially habitable exoplanets, enabling a large-scale survey of atmospheric variety on worlds that could host life. Every observation improves our knowledge of how planetary atmospheres develop and the conditions required for life to begin and survive. This expanding database of exoplanet atmospheres is uncovering patterns that aid in defining the essential criteria for habitability. For example, some planets have abundant water vapor, while others seem arid even within their star's habitable zone. These variations could be due to different formation paths, stellar conditions, or the inherent diversity of planetary evolution. This method of comparing exoplanets is similar to the one that transformed our knowledge of planet formation in our solar system. The study of the varied planets around our Sun, such as Venus and Titan, allowed scientists to form theories about planetary development in diverse circumstances. Applying this comparative strategy to exoplanets offers new perspectives on planetary processes under conditions not found locally. The search for biosignatures on planets like K2-18b is also stimulating progress in laboratory science with applications beyond astronomy. To comprehend molecular behavior in the extreme environments of these worlds, new experimental methods are needed that advance high-pressure chemistry and physics. Findings from these experiments not only aid in interpreting exoplanet data, but also deepen our knowledge of basic chemical processes in conditions similar to those inside planets. K2-18b's atmospheric chemistry includes intriguing reactions impossible under Earth-like conditions. Its high pressures, hydrogen-rich environment, and unique ocean chemistry could facilitate molecular interactions never before seen in labs on Earth. Investigating these phenomena necessitates new experimental and theoretical approaches, thereby broadening our foundational understanding of chemistry and physics. The potential biological consequences of these unusual chemical processes are especially compelling. While life on Earth is adapted to our planet's specific conditions, biological principles could function differently in the environments of other worlds. High atmospheric pressures might permit biological functions that are not possible on Earth, and hydrogen-based chemistry could offer energy sources not available to life here. The study of Earth's extremophiles, organisms that flourish in environments previously considered uninhabitable, supports this idea. Examples like bacteria in acidic hot springs, archaea in high salinity water, and microbes in deep-sea trenches show life's incredible adaptability. Such discoveries suggest what could exist in the even more severe conditions of remote exoplanets. Research on terrestrial extremophiles is essential for interpreting potential biosignatures on planets such as K2-18b. If organisms from Earth can survive in conditions like those on these exoplanets, it supports the possibility of life there. If they cannot, it implies that any local life would be fundamentally different from ours. Laboratory experiments testing the survival of terrestrial life in these alien conditions are producing unexpected outcomes. Certain microorganisms display significant resilience to high-pressure hydrogen atmospheres, continuing metabolic functions in environments lethal to most known organisms. This research indicates that the distinction between habitable and uninhabitable environments may not be as rigid as once believed. These implications affect not only single organisms, but also the dynamics of entire ecosystems. Should life exist in such conditions, the resulting ecosystems would likely function based on principles distinct from those that govern Earth's biosphere. The energy sources, nutrient cycles, and evolutionary pressures on other worlds would be unfamiliar to us, possibly resulting in biological structures unlike anything seen on Earth. The prospect of finding such alien ecosystems raises significant questions about how we detect and study life beyond our planet. Current research on biosignatures is mainly focused on the molecules and processes of life on Earth. However, truly alien life could produce chemical signs that we would not identify as biological. The challenge is not only to find life, but also to recognize it when it follows principles we have not yet encountered. This recognition difficulty is especially pronounced when considering the chance of false negatives in biosignature searches. While much effort is spent avoiding false positives, where non-biological processes look like signs of life, the reverse situation could be just as problematic. If alien life creates biosignatures that are completely different from those on Earth, we might miss real evidence of life, simply because it does not meet our expectations. Observations of K2-18b have demonstrated this difficulty, revealing atmospheric chemistry that cannot be easily classified as either biological or non-biological. The strange amounts and mixes of molecules found in the planet's atmosphere could indicate either unusual life forms or unknown atmospheric phenomena. To tell the difference, we must broaden our scientific models to include possibilities we do not yet understand. This expansion of scientific knowledge is one of the most exciting parts of exoplanet research. Each new planet we examine presents possibilities we had not considered, compelling us to challenge our assumptions and create new theories for observations that do not fit current models. This process is similar to the major shifts in scientific thought that have historically changed our view of the natural world. The study of K2-18b is also showing how important long-term observation is for understanding exoplanet atmospheres. Planetary atmospheres are not static systems with unchanging chemical makeups, as one might conclude from a single observation. They are dynamic and can change significantly over time. Weather seasons and geological events all affect atmospheric chemistry in ways that a single observation during a transit could overlook. The short views of exoplanet atmospheres we get during transits are just snapshots of complex, changing systems. To know if observed chemical signatures are stable or temporary, multiple observations over months or years are needed. This time-dependent nature of atmospheric analysis adds another level of difficulty to the interpretation of potential biosignatures. Future studies of K2-18b will need to account for these changes over time, while also increasing the certainty of any potential biosignature discoveries. The observation plans being created for follow-up studies are a balance between the want for quick results and the requirement for a thorough analysis. Each observation uses valuable telescope time that might otherwise be spent on other potentially habitable planets, requiring researchers to balance between studying many worlds and studying one in great detail. The scheduling difficulties in K2-18b research are part of a larger problem in modern astronomy, where the demand for time on advanced telescopes is much greater than the supply. The James Webb Space Telescope gets proposals for far more observation hours than it can offer, which means review committees must make tough choices about which projects to prioritize. The potential importance of finding biosignatures gives K2-18b researchers a compelling case for telescope time, but they must compete with other important research in all fields of astronomy and astrophysics. This competition for observation time has encouraged new developments in how observations are planned and how data is analyzed. Researchers are creating ways to get the most information from limited observation periods, employing advanced statistical methods and machine learning to extract every possible insight from data that is difficult to obtain. The limitations of telescope scheduling have unexpectedly sped up progress in data analysis, which helps all areas of astronomical research. The technological needs for studying planets like K2-18b are also leading to the creation of next-generation space telescopes designed specifically for studying exoplanets. These future telescopes will overcome many of the current challenges in biosignature searches, offering the sensitivity and stability required for conclusive discoveries of life beyond Earth. The Nancy Grace Roman Space Telescope, set to launch in the next few years, will support the James Webb Telescope with capabilities suited for different areas of exoplanet research. While James Webb is excellent for detailed atmospheric study of known exoplanets, Roman will scan large sections of the sky to find new planets and pinpoint the best ones for further investigation. The way these instruments work together could transform our capacity to locate and study worlds that might support life. Ground-based telescopes are also being improved to handle the difficulties of studying exoplanet atmospheres. The extremely large telescopes now being built will offer the ability to collect more light than ever before and provide higher resolution, allowing for detailed studies of light that support observations from space. The use of both space and ground-based resources could furnish the several types of proof needed to conclusively confirm the detection of biosignatures. These technological developments are the result of significant financial commitments by the international scientific community to answer basic questions about life in the universe. Government space agencies, international partnerships, and private entities are spending billions of dollars to construct the instruments required to find and study life on other worlds. This spending is driven not only by scientific curiosity, but also by the understanding that such findings could completely change our view of our place in the universe. The benefits from this spending are not limited to astronomy and could help all of society. The technologies created to find trace gases in exoplanet atmospheres can be used for environmental monitoring, medical diagnosis, and industrial process management. The data analysis methods first developed for astronomy are being applied in fields from finance to healthcare. The international partnerships formed for major space missions build relationships that make it easier to work together on other global challenges. However, the greatest importance of finding life beyond Earth is not about new technologies or economic gains. Such a discovery would be a major increase in what humanity knows and would affect how we view ourselves and our connection to the cosmos. The psychological and philosophical effects would be felt in all parts of human culture, including science, religion, art, and literature. The current research on K2-18b's potential biosignatures is creating both excitement and debate in the scientific community. Every new analysis of the data seems to show more complexity instead of providing clear conclusions. The atmosphere of this faraway world seems to be much more complex than first thought, with chemical activities that do not align with current scientific models. This complexity may be the most significant finding from the K2-18b research. The belief that exoplanet atmospheres would be fairly simple systems controlled by well-known physics and chemistry is being shown to be incorrect, as observations show the surprising variety and complexity of atmospheric processes on distant worlds. Each new discovery challenges our scientific models and compels us to broaden our understanding of what is possible in the chemistry of planetary atmospheres. Advancing our understanding is the core of scientific progress, pushing the limits of human knowledge to drive history forward. Regardless of whether K2-18b hosts life or is an example of unusual atmospheric chemistry, the research has already expanded our knowledge in ways that will shape future science. The methods created, theories broadened, and questions posed will direct future studies on the abundance of life in the cosmos and the variety of worlds in our galaxy. Awaiting future observations to solve the puzzle of K2-18b's atmosphere places us within a significant human endeavor. The search for extraterrestrial life is both a result of centuries of scientific progress and the start of a potentially remarkable new phase in human knowledge. As advanced instruments monitor the cosmos, we are on the verge of discoveries that could change our understanding of life's role in the universe. Researchers in laboratories and observatories globally are conducting highly complex astronomical analyses, navigating the balance between statistical certainty and possibility. The 3 sigma detection of dimethyl sulfide on K2-18b is more than a statistic. It represents the fine line between a groundbreaking discovery and scientific prudence, distinguishing the extraordinary from the unusual. In practice, a 3 sigma result means that if the same observation were repeated 1,000 times, a false positive would be expected only 3 times, while this level of confidence is considered sufficient for publication. In most scientific fields, the profound implications of finding extraterrestrial life require a higher standard from the scientific community. Researchers are aiming for the 5 sigma threshold, which lowers the probability of a false positive to less than 1 in 3.5 million, the same standard used to announce the discovery of the Higgs boson. Because extraordinary claims need extraordinary evidence, researchers must determine if they can gather enough observational data on K2-18b to meet this statistical requirement. Achieving 5 sigma confidence involves more than just longer observation times. Researchers must also manage systematic errors, instrumental issues, and the limitations of studying a world at the limit of our technology. Every new observation needs careful planning to maximize scientific results and minimize the risk of error or misinterpretation. Dr. Madhusudan's team has created a specific plan to reach this higher level of statistical confidence. The plan identifies specific wavelength ranges for the strongest DMS signature, the most sensitive instruments for its detection and observation strategies to rule out other explanations for the signals. This plan necessitates 16 to 24 additional hours of observation time on the James Webb Space Telescope, a significant use of a valuable scientific resource. The high demand for observation time on the telescope shows its transformative effect on many fields of astronomy. While characterizing exoplanet atmospheres is just one of its functions, the possibility of finding biosignatures has attracted significant global interest. The telescope is scheduled months ahead, with numerous research teams vying for access to its unique capabilities. This scheduling difficulty has led the astronomical community to create new systems for prioritizing observations according to their potential scientific importance. Discovering extraterrestrial life would be a major achievement, but so would detecting the first galaxies or analyzing the atmospheres of planets in our solar system. Committees allocating telescope time must balance these competing goals and ensure the efficient use of resources. The international collaboration behind the telescope, a partnership between NASA, the European Space Agency, and the Canadian Space Agency, adds complexity to planning. Coordinating observations across different time zones and organizations demands significant planning and diplomacy comparable to the technical challenges of operating the telescope. The potential benefits of confirming biosignatures on K2-18b warrant the significant effort involved in these observations. Such a detection would be more than just finding extraterrestrial life. It would confirm a new method for seeking habitable worlds, broadening the definition of habitability beyond the conventional focus on Earth-like planets around Sun-like stars. This would have transformative implications for astrobiology. If life can exist in the hydrogen-rich oceans of Haitian worlds, the number of potentially habitable planets in our galaxy could increase significantly. Sub-Neptune planets like K2-18b are a common type of discovered world, and their red dwarf host stars are the most numerous in the Milky Way. This combination implies that habitable environments could be more common than an Earth-focused viewpoint suggests. A significant change in habitability estimates would deeply affect the Drake equation, which astronomers use to estimate the number of communicative civilizations in our galaxy. If life can exist and evolve intelligence on Haitian worlds, the universe could be much more populated than previously thought. The lack of signals in searches for extraterrestrial intelligence could be due to limitations in our search methods rather than a lack of technological civilizations. The potential for widespread life on Haitian worlds is already changing how researchers search for technosignatures, which are observable signs of alien technology. Traditional SETI has concentrated on radio signals from civilizations assumed to be like ours, but the discovery of potentially habitable sub-Neptunes implies that technological species could evolve in conditions very different from Earth's. Civilizations from the high-pressure, hydrogen-rich environments of Haitian worlds could develop technologies based on unfamiliar principles, with communication energy and travel methods so different from ours that we might not identify them as artificial. This issue of recognition presents significant challenges for techno-signature research going beyond conventional radio astronomy. Searching for artificial signals from K2-18b has its own challenges. Its distance of 124 light-years means a round-trip communication would take almost 250 years, making real-time conversation impossible within human timeframes. Even if intelligent life on the planet were trying to communicate, the exchange would occur over time, periods longer than the lifespan of civilizations. However, simply knowing life existed on K2-18b would fundamentally change humanity's relationship with the universe. We would understand that we are not alone in the universe or unique in our capacity for consciousness and technology. The psychological effect would be comparable to the Copernican revolution, which moved Earth from the universe's center, compelling humanity to rethink its place in the cosmos. The cultural consequences would also be profound. Religious traditions would face the challenge of adapting their cosmologies to accommodate life that evolved in conditions different from those in their core texts. Philosophers would consider if consciousness and intelligence are inevitable consequences of cosmic evolution or rare accidents specific to certain circumstances. Artists and writers would draw inspiration from imagining life forms suited to environments beyond Earth. Educational systems would be tasked with preparing students for a universe known to contain various forms of life. The discovery would likely prompt a major investment in science education, as societies would see the need for citizens who could understand and contribute to a wider cosmic perspective. New academic fields would arise, combining astrobiology, comparative planetology, and xenopsychology in ways that do not currently exist. The economic effects would also be significant. The space industry would grow rapidly as governments and private entities invested in the telescopes, spacecraft, and technologies required to examine other potentially inhabited worlds. Confirming life on K2-18b would shift astrobiology from a speculative discipline to a practical science with direct uses for understanding and possibly communicating with alien life. Research and development would concentrate on creating technologies for the in-depth study of distant biospheres, which could include interstellar missions to nearby habitable planets. Although the immense distances would make such missions exceptionally difficult, the certainty that life exists on reachable targets would justify funding for advanced propulsion technologies and autonomous spacecraft. The biotechnology sector would also be transformed as scientists work to understand how life could function in conditions vastly different from Earth's. The study of extremophiles would be broadened to include laboratory simulations of Haitian environments, which might reveal new biochemical pathways and molecular processes applicable to medicine, agriculture, and industrial biotechnology. Perhaps the most profound impact would be on human consciousness. The confirmation of life on K2-18b would act as a cosmic mirror, reflecting our own existence's remarkable nature, while showing that life is not exclusive to our planet. This discovery would be both humbling and inspiring, serving as a reminder of our cosmic place while celebrating the phenomenon of life itself. Ongoing analysis of K2-18b's atmospheric data, continues to show new levels of complexity, challenging our models of planetary atmospheric chemistry. Every improvement in analytical methods seems to find more molecular species and chemical processes that do not align with current theories, indicating the planet's atmosphere is a much more dynamic and complex system than first thought. A recent re-examination of spectroscopic data suggests the presence of other organic molecules besides the notable DMS detection traces of complex hydrocarbons, sulfur-based compounds, and nitrogen-containing species indicate an atmospheric chemistry as complex as Earth's biosphere. It remains an open question whether these molecules are from biological activity or unusual non-biological processes. The isotopic ratios of atmospheric components offer another method for understanding K2-18b's chemistry and potential biology. On Earth, biological processes often favor lighter isotopes, leaving distinct signatures in atmospheric samples. Similar isotopic fractionation on K2-18b could offer more evidence for life. But interpreting these signals requires knowing how isotopic processes might work in a High-Cean environment. The difficulty of isotopic analysis is especially great for spectroscopic observations over interstellar distances, as the precision needed to find isotopic variations in exoplanet atmospheres is at the limit of current technology. Future space telescopes will require even more sensitivity and resolution to make such measurements routinely. The timing of K2-18b's atmospheric chemistry introduces another layer of difficulty for researchers. The planet's 33-day orbit suggests atmospheric conditions could change significantly based on its location relative to its star. Any seasonal variations could affect the rates at which chemicals are produced and destroyed, influencing the interpretation of transit observations. Understanding these changes over time demands numerous observations throughout the planet's orbit, possibly over several years. Such long-term monitoring requires significant telescope time, but could offer vital information about the stability of potential biosignature molecules. Detecting signals that vary over time might strengthen the case for a biological origin, as life often creates cyclical patterns in atmospheric chemistry. The three-dimensional structure of K2-18b's atmosphere is another area of study. Current observations give an average view across the planet's visible disk during transits, but the actual atmospheric composition probably changes with altitude, latitude, and local conditions. Future observational methods may be able to map these differences, creating more detailed images of atmospheric structure and chemistry. Advanced models are starting to investigate how atmospheric circulation could affect the distribution of potential biosignature molecules. The planet's dense hydrogen atmosphere might sustain complex circulation patterns caused by solar heating and its rotation. These movements could move chemical species between different atmospheric regions, causing compositional variations that could be detected with sensitive observations. The magnetic field around K2-18b is mostly unknown, but could be vital for protecting a potential biosphere from harmful stellar radiation. Red dwarf stars are known for powerful flares that could erode planetary atmospheres over time, if not deflected by strong magnetic fields. The existence of complex atmospheric chemistry on K2-18b could be indirect evidence of magnetic protection. Theoretical studies of sub-Neptune planets indicate they could generate strong magnetospheres if their interiors contain conductive materials. The unusual forms of water ice that might exist under the high pressures inside K2-18b could have different electrical properties than regular ice, potentially allowing for unique magnetic dynamo processes. The interaction between a potential magnetic field and the thick hydrogen atmosphere on K2-18b could lead to distinct chemical environments Charged particles trapped in magnetic field lines might trigger chemical reactions that create or eliminate biosignature molecules in ways not yet studied. Understanding these processes is key to interpreting observations and differentiating between biological and physical causes for the atmospheric chemistry. The search for other Hycean worlds in the K2-18 system has started, as planetary systems frequently have multiple planets with similar features. If K2-18b formed in a way that allowed it to have a hydrogen-rich atmosphere and a possible ocean, other planets in the system may have developed similarly. The discovery of multiple potentially habitable worlds orbiting one star would offer valuable data for comparing and understanding planet formation and evolution. Methods created for analyzing K2-18b are now being used on other sub-Neptune exoplanets within their star's habitable zones. The study of each new world enhances our knowledge of the varied atmospheres of these planets. While some display distinct signs of water vapor and intricate chemistry, others seem to possess simpler atmospheric makeups. These variations could be due to different formation histories, stellar conditions, or the natural diversity that arises from planetary evolution. By comparing multiple Hycean candidates, researchers are starting to identify patterns that may help forecast which newly found exoplanets have a higher probability of containing biosignatures. Elements like planetary mass, orbital distance, stellar age, and system structure all seem to affect atmospheric composition in ways that are just beginning to be understood. This expanding base of knowledge is essential for prioritizing subsequent observations as additional potentially habitable worlds are identified. Research on K2-18b fosters collaboration among academic fields that typically do not interact. Atmospheric chemists and marine biologists are working together to comprehend how life could adapt to high-pressure water environments. Geophysicists are partnering with astrobiologists to create models of the internal structures of sub-Neptune planets. Meanwhile, computer scientists are creating machine learning algorithms designed to detect faint biosignature signals within noisy spectroscopic data. This exchange of expertise is producing knowledge that a single field could not attain on its own. The K2-18b study has become a test case for interdisciplinary scientific teamwork, showing that complex issues demand a variety of viewpoints and skills. The effectiveness of this method is shaping how major scientific organizations structure their research and distribute resources for tackling other significant challenges. The educational influence of the K2-18b research reaches beyond academic settings to include public outreach and science communication. The prospect of finding life elsewhere has engaged the public's imagination more than typical astronomical findings. Around the world, science museums, planetariums, and educational organizations are using the K2-18b narrative in programs meant to encourage interest in science and space exploration. For science educators, the difficulty lies in conveying the uncertainty and intricacy of the research while keeping the public interested and excited. The account of K2-18b serves as an excellent example of how science operates on the cutting edge of knowledge, where new observations question current theories and compel scientists to broaden their perspectives. Educating students about these ideas prepares them for a reality in which scientific understanding constantly develops and grows in light of new findings. The international scope of K2-18b research has generated chances for global cooperation that go beyond the immediate scientific inquiries. Scientists from numerous countries are providing observations, analytical methods, and theoretical perspectives to study this remote planet. The collaborative systems formed for this work are now being utilized for other significant scientific endeavors that need international coordination and shared resources. Such international partnerships show how basic scientific inquiries can bring together researchers from different political and cultural backgrounds. The quest for extraterrestrial life is a shared human effort that goes beyond national concerns and ideological divides. The spirit of cooperation developed through projects like the K2-18b research may act as a blueprint for tackling other worldwide problems that demand continuous international teamwork. While awaiting further observations to resolve the questions about K2-18b's atmospheric chemistry, we are taking part in a major scientific pursuit. Whether the planet is found to support life or is merely an unusual case of atmospheric chemistry, this research has already changed our perception of cosmic possibilities and shown humanity's ability to advance knowledge. The light traveling from K2-18's star contains potential answers to fundamental questions about our existence. Every photon arriving at our instruments is a signal from a remote and foreign world, its existence questioning our ideas about life and habitability. Between observations as advanced instruments monitor this planet, we are situated between the known and the unknown, weighing the familiar chemistry of Earth against the potential chemistries of worlds with hydrogen-rich oceans. The universe has already shown a surprising variety of planetary atmospheres and unusual chemistry in previously unimagined conditions. K2-18b could provide the ultimate surprise by confirming that life can thrive in environments that expand our understanding of the relationship between chemistry and biology. This narrative is developing in laboratories and observatories globally, where researchers strive to gain all possible information from observations that test the limits of technology. Each new analysis uncovers further complexities. Every theoretical model presents new options, and each observation moves us slightly nearer to answering a fundamental human question. This dedicated search for knowledge highlights not only scientific progress, but also our species' best attributes: immense curiosity, a dedication to understanding, and the bravery to pursue answers that could alter our perception of ourselves and our position in the universe. The systematic process needed to confirm these remarkable findings demonstrates the meticulous character of groundbreaking science. Before scientists can suggest the possibility of genuine evidence for extraterrestrial life, every measurement must be checked, every possible error removed, and every other explanation investigated. The threshold for statistical significance that distinguishes an interesting observation from a confirmed discovery is now the subject of a major international scientific focus. The computational demands of this work are immense. Contemporary spectroscopic analysis depends on algorithms that can process wavelength data with an accuracy of parts per billion, separating true molecular signals from numerous interferences over interstellar distances. Each transit observation yields millions of individual data points, with each point holding a piece of information on K2-18b's atmosphere. To find significant patterns within this large volume of data, computational methods that test the limits of current technology are necessary. Machine learning systems developed for astronomy are being trained to see patterns that human analysts might overlook. These artificial intelligence systems are taught to recognize the slight combinations of spectral characteristics that separate actual biosignatures from equipment-related errors or contamination from Earth's atmosphere. The algorithms need to consider factors ranging from small temperature changes in the telescope to the intricate physics of starlight's interaction with atmospheric molecules over 124 light-years. The level of precision required for this analysis is difficult to grasp from a human viewpoint, comparable to trying to hear a single whisper within the noise of a million-person crowd. Researchers face a significant challenge in their search for the faint molecular signatures that could signal biological processes in K2-18b's atmosphere. Underlying these technical difficulties is a more fundamental question about the nature of life itself. The molecules potentially found on K2-18b are in concentrations thousands of times higher than what is observed in Earth's atmosphere. If biology is responsible for these signatures, it suggests life operating on a scale far greater than our experience on Earth. This possibility extends beyond mere detection, questioning our fundamental assumptions about how biological systems operate. For example, consider the energy needed to produce dimethyl sulfide at the concentrations potentially seen on K2-18b. On Earth, this molecule is a byproduct of the metabolic processes of marine phytoplankton, but the total global output is minor compared to what might be occurring on that world. If life is indeed driving K2-18b's atmospheric chemistry, its scale and efficiency would make our planet's biosphere appear quite small in comparison. Theoretical models being created to account for these observations are moving into new territory where biology and planetary science intersect. Scientists are trying to figure out how large oceanic ecosystems could operate under atmospheric pressures many times greater than Earth's. In such conditions, the physics of gas exchange between organisms and their environment would be completely different, possibly allowing for biological processes that are not possible in our low-pressure atmosphere. The chemical pathways available to potential life in K2-18b's hydrogen-rich environment present another new area in our understanding of life's possibilities. Life on Earth functions within the confines of an oxygen-rich atmosphere, which makes certain chemical reactions favorable and others impossible. The hydrogen-based chemistry of a Hycean world could permit entirely different metabolic processes, possibly sustaining life forms that use chemical energy sources unavailable to terrestrial organisms. Laboratory experiments designed to evaluate these theoretical concepts are yielding surprising information about life's ability to adapt to extreme environments. Researchers are placing terrestrial microorganisms in simulated Hycean conditions, subjecting them to high-pressure hydrogen atmospheres and observing their survival and metabolism. The findings indicate that the line between habitable and uninhabitable may be more flexible than previously thought. Some bacteria not only survive in hydrogen-rich high-pressure environments, but in some cases exhibit increased metabolic activity. While this does not confirm life on K2-18b, it does show that the conditions on Hycean worlds could be compatible with biological functions. These experiments are broadening our knowledge of life's basic needs and providing essential context for analyzing atmospheric data. The isotopic signatures within K2-18b's spectroscopic information provide another possible way to determine if the observed chemistry is from biological or purely physical sources. On Earth, living things tend to use lighter isotopes of elements like carbon and sulfur in their biochemical makeup. This isotopic fractionation leaves behind distinct patterns that can act as evidence of biological activity even if the organisms cannot be seen directly. To detect these isotopic signatures in the atmospheres of exoplanets, spectroscopic methods must be pushed to their absolute limits. The differences in wavelength between isotopic versions of a molecule are frequently smaller than the uncertainties in current measurements. Although future space telescopes are being designed specifically for such tasks, today's instruments lack the necessary precision for a definitive isotopic analysis over such vast distances. The changes over time in K2-18b's atmospheric chemistry introduce another layer of difficulty to the interpretation. Because the planet has a relatively brief orbital period, its atmospheric conditions could change considerably as it travels around its red dwarf star. These fluctuations could impact chemical production rates, how the atmosphere mixes, and the stability of potential biosignature molecules, thereby affecting how we interpret single-transit observations. Long-term observation campaigns are being organized to monitor how K2-18b's atmospheric makeup shifts over several orbits. This type of observation could show if the potential biosignature molecules display the kind of time-based variation expected from biological activity. On Earth, the atmospheric concentrations of gases produced by life often follow seasonal patterns, daily cycles, and changes in response to ecological events, all of which create unique temporal signatures. The magnetic environment of K2-18b is one of the biggest unknowns when evaluating its potential for life. Red dwarf stars are known for their strong flare activity, which can blast nearby planets with high levels of radiation and charged particles. Without sufficient magnetic protection, these stellar events could slowly erode a planet's atmosphere, making long-term habitation impossible even if other conditions are favorable. How a magnetic field is generated in a sub-Neptune planet like K2-18b relies on intricate processes deep inside it. The unusual states of matter that might exist under the immense pressures in these worlds could have electrical properties unlike anything on Earth. Some theories propose that superionic ice, a phase of matter where hydrogen ions move through a crystal oxygen lattice, could facilitate magnetic dynamo effects not seen in our solar system. If K2-18b does have a strong magnetic field, the interaction between this shield and its dense hydrogen atmosphere could result in unique chemical settings not found elsewhere in our cosmic vicinity. Charged particles caught in magnetic field lines might drive atmospheric chemistry in ways that have not been studied in labs on Earth. Understanding these mechanisms is vital for separating biological explanations for the observed atmospheric composition from purely physical ones. As astronomers grasp the potential astrobiological importance of Hycean planets, the search for other worlds like K2-18b has grown. Dozens of sub-Neptune planets that orbit in the habitable zones of their stars have been flagged as potential subjects for atmospheric study. Each new planet observed contributes to our expanding database on the atmospheric variety of these worlds, uncovering patterns that could help us determine the key factors for creating potentially habitable environments. Some of these Hycean candidates display spectroscopic signs of water vapor and intricate atmospheric chemistry akin to that seen on K2-18b. Others seem to have much simpler makeups, primarily hydrogen and helium, with little indication of the complex chemistry that might suggest surface oceans or life. The variations might be due to different formation histories, stellar conditions, or the natural diversity that arises from planetary evolution under distinct circumstances. Comparative analyses of several Hycean worlds are starting to show connections between planetary traits and atmospheric makeup, which could inform future searches for biosignatures. Planets within certain mass ranges, at specific orbital distances, and of particular stellar ages seem more likely to exhibit signs of complex atmospheric chemistry. These trends are shaping theoretical models of Hycean planet formation and evolution, and assisting researchers in prioritizing which targets to select for in-depth observation. The interdisciplinary cooperation needed to make sense of K2-18b has led to novel partnerships among scientists who typically do not work together in conventional academic environments. Atmospheric chemists who specialize in Earth's stratosphere are collaborating with marine biologists who study deep-sea ecosystems. Planetary scientists are working with biochemists to understand how metabolic processes might function in alien conditions, while computer scientists are creating specialized algorithms to detect faint patterns in astronomical data. This combination of expertise is yielding insights that a single discipline could not achieve alone. Interpreting the atmospheric observations of K2-18b is a complex task that requires knowledge ranging from the quantum mechanical interactions between photons and molecules to the ecological principles that govern ecosystem stability. The successful combination of such varied knowledge provides a new model for approaching complex scientific problems that involve multiple fields. The technological developments from K2-18b research are already being applied in areas beyond astronomy. Highly sensitive spectroscopic techniques developed to find trace gases in exoplanet atmospheres are now being adapted for environmental monitoring, medical diagnostics, and industrial process control. Similarly, the data analysis methods created to extract weak signals from noisy astronomical observations are proving useful in fields such as seismology and financial modeling. Machine learning algorithms trained on astronomical spectra are being repurposed for use in materials science, helping to identify the composition of unknown substances from their optical properties. The statistical techniques designed to evaluate the significance of potential biosignature detections are also being used in medical research, where comparable methods are employed to assess the effectiveness of new treatments based on limited clinical trial data. The international cooperation promoted by the research on K2-18b has built collaborative networks that reach far beyond the specific scientific questions at hand. Researchers from numerous countries are contributing observational data, analytical skills, and theoretical insights to the study of this distant world. The partnerships created for this research are being utilized for other major scientific projects that demand global coordination and the sharing of resources. These collaborations show how basic questions about life and our position in the universe can unite scientists across political and cultural divides. The search for life beyond Earth is a shared human effort that surpasses national interests and ideological differences. The cooperative spirit seen in the K2-18b research could act as a template for tackling other global challenges that need sustained international collaboration. The educational effect of this research is felt in classrooms and public forums around the world, where the story of K2-18b is used to show how science functions at the forefront of human knowledge. Students are learning about the iterative process of testing hypotheses, the value of statistical precision, and the collaborative character of modern scientific inquiry. The uncertainty and complexity involved in the research process offer valuable lessons on how knowledge is advanced through careful observation and analysis. Science museums and planetariums have created interactive exhibits that let visitors explore the difficulties of detecting biosignatures on distant planets. These programs assist the public in understanding both the technical challenges of such research and the profound meaning of any potential discoveries. The interest sparked by K2-18b's story is inspiring a new generation of students to enter careers in astronomy, astrobiology, and related fields. Confirming life on K2-18b would have economic consequences that extend beyond academic research, affecting entire industries and national economies. The space sector would see significant growth as governments and private entities invested in telescopes, spacecraft, and technologies to study other potentially inhabited worlds. Biotechnology companies would endeavor to learn how life might function in conditions vastly different from Earth's, possibly leading to the discovery of new biochemical pathways with uses in medicine and industry. Such a confirmation would also stimulate large-scale investments in fundamental research across many scientific disciplines. Universities would create new departments centered on astrobiology and comparative planetology. Government agencies would initiate major research programs to comprehend the implications of widespread life in the universe. Private foundations would finance expeditions to study extremophile organisms on Earth as analogues for possible alien life forms. However, the most significant impact would be on human consciousness itself, requiring our species to address questions about our place in a universe that contains multiple forms of life. The philosophical effects would be felt in every part of human culture, from religion and ethics to art and literature. We would have to create new conceptual frameworks for our relationship with alien life and for our responsibilities as cosmic citizens. The ongoing analysis of K2-18b's atmospheric data continues to show new layers of complexity that challenge current theoretical models. Each improvement in analytical techniques seems to reveal more molecular species and chemical processes that do not fit clearly into either biological or purely physical classifications. The planet's atmosphere is proving to be a much more sophisticated system than first thought, with chemical interactions that follow principles we are just starting to understand. A recent reanalysis has shown potential signs of complex organic molecules beyond the debated DMS detection trace amounts of hydrocarbons. Nitrogen-containing compounds and unusual sulfur species form a chemical inventory that is nearly as diverse as Earth's biosphere. The central question for future research is whether these molecules are the result of biological metabolism or of previously unknown non-biological processes. The three-dimensional structure of K2-18b's atmosphere is another area of study. Current observations provide data averaged over the entire visible surface of the planet during its transit, but the actual atmospheric composition likely changes considerably with altitude, latitude, and local weather. Future observational methods may be able to map these changes, offering more detailed images of atmospheric dynamics and chemistry. Advanced computer models are being created to simulate the complex interactions between K2-18b's dense hydrogen atmosphere and its theoretical underlying ocean. These simulations must consider atmospheric circulation patterns caused by stellar heating, chemical reactions at different pressure levels, and the movement of molecules between atmospheric layers. The models suggest that hydrogen atmospheres might be more dynamic and layered than previously believed. The magnetic field around K2-18b could be critical in determining the planet's atmospheric chemistry and its long-term habitability. Red dwarf stars are known for emitting powerful stellar flares that could erode planetary atmospheres over geological time, if not deflected by a strong magnetic field. The existence of complex atmospheric chemistry on K2-18b could be evidence of such magnetic protection, though the direct detection of exoplanet magnetic fields is not yet possible. Theoretical studies indicate that the exotic materials under extreme pressure inside K2-18b might generate magnetic fields through processes different from those in our solar system. The interaction between such magnetic fields and the planet's hydrogen-rich atmosphere could form unique chemical environments driving atmospheric chemistry in ways not seen on Earth. Understanding these processes is vital for interpreting observations and distinguishing between biological and purely physical sources of atmospheric composition. The changes in K2-18b's chemistry over time add another layer to the challenge for researchers. The planet's 33-day orbit means that atmospheric conditions could vary greatly as it moves through different orbital phases. Any seasonal effects could impact chemical production rates and atmospheric stability, which would affect the interpretation of individual observations. As we are at a significant point in human history, observing the constellation Leo, where K2 Wu18b orbits its distant star, we contemplate both profound ideas and possibilities. Whether this hydrogen-covered world contains the first confirmed life beyond our solar system or simply displays the most unusual atmospheric chemistry ever seen, K218b has already altered our understanding of what is possible in the cosmos. The light carrying these potential biosignatures is still on its long journey to our telescopes. With each night we move closer to answers that could fundamentally change